So hello everyone, and I hope everybody is staying healthy, and thank you for participating to our virtual edition of the workshop. So today what I'm going to talk about, I will just give you some basic introduction about electron-phonon interaction. So I will start by telling you where do we see electron-phonon interaction in experiments, and how to accurately and effectively calculate electron-phonon interactions with the EPW code. And then in the second part, I will discuss briefly the Migdal-Eliashberg formulas for superconductivity, which allows one to calculate superconducting properties with anisotropic resolution. And then I will discuss the Boltzmann transport equations, which enables one to study carrier transport in metals and semiconductors. So to understand why electron-phonon interaction are important, as I said, we will first look just at some manifestation of electron-phonon interaction in experiments. And as you will see today, calculations of electron-phonon interactions are notoriously more challenging than standard total energy calculations. But in the last 5 years, the demand for such calculations has increased tremendously. And this is because the interactions between electrons and phonons dominate many materials properties of technological interest. So for example, the temperature dependence of charge transport coefficient in metals and semiconductors relies on the interaction between electrons and phonons. The same, the absorption and emission of light in indirect band gap semiconductors and insulators. The formation of Cooper pairs in conventional superconductors, and for example, the ultra-fast dynamics of photoexcited carriers. So all these properties are basically essential when we want to design materials that will underline future technologies, including solar cells, touch screens, superconducting cables, and other devices. So now, since today we are going to look at some material properties defined by the electron-phonon interactions in our tutorials, I will first want to tell you a bit how the electron-phonon matrix elements look like, and as I said, how we can accurately calculate them with the EPW code. And here, this is the standard expression of the electron-phonon matrix elements in DFT. So these two things on the left and right, these are the periodic part of the wave functions of the Kohn-Sham wave function. And the object here in the middle, this is the variation of the Kohn-Sham potential with respect to the displacement of every atom according to a vibrational mode. So this object now is quite complicated and contains a lot of information. For example, it has the 0-point amplitude, which depends on the mass of every atom and the vibrational and the frequency for each vibrational mode. Then we need to tell the atoms in which direction to move. So this is basically the phonon polarization, which is the eigenvector of the dynamical matrix. And then we have, as I said, the change in the self-consistent potential with respect to the displacement of every atom in the cell. And I would also like to emphasize that the potential also involves a periodic modulation, which essentially allows one to access wavelengths that go beyond the unit cell. So when we do density functional perturbation calculation, we can access wavelengths beyond the unit cell by still performing unit cell calculation. And that's the power of DFTP. So now, I also, before showing a bit more details about how to calculate electron-phonon matrix elements, I want to say a few things about the problems that exist in these calculations. And as an example here, I'm just showing the expression for the electron lifetime in metals in the adiabatic approximation. So basically, if you want to calculate this quantity, first of all, you need to perform an integral over the phonon wave vectors in the Brillouin-zone. And integrals means that we need to sum over a lot of phonons wave vectors. And typically, since there is this delta function here, it means that we need to sum, in order to obtain converged results, we need typically something of the order of 100,000 K vectors. And this number would not be very large if we would do simple calculations, but you need to keep in mind that this basically means that for each Q vector, we basically require to do a separate phonon calculation, so a separate DFTP calculations. Now, also, if you want to calculate properties like mobilities, and you will see later on the expression for mobility, we need to take into account the lifetime of many electrons, not just one electron. So this means that we will need to perform this integral for many K vectors and then do an average over over them. So this basically what it means, what really means is that in order to, you need to be able to compute electron-phonon matrix elements for very dense K and Q meshes. And the way that has become established to do these calculations efficiently and accurately is to use the Wannier functions. And I'm not going to go into details about Wannier functions, since you have already seen this during the previous day, but what I want to just remind you that you can basically perform a unitary transformation of the Bloch function to obtain a new function with the properties that this is localized. So for example, if you take a Bloch function, which is some type of atomic like orbital modulated by a plane wave, you can basically extract, you can do this transformation and extract the atomic character of these objects. And the most important thing is that you can go reversibly from right to left without losing any information. So now, if you remember that I said that the electron-phonon matrix element contains 3 parts, you can imagine we can do a transformation for each of that object, the Bloch functions, and on the left, the Bloch function on the right, and then the change in the potential. And we can formalize that by finding an expression for the electron-phonon matrix elements in the Bloch representation as a function of the phonon matrix elements in the Wannier representation, which are shown here in red, and that's the expression for the electron-phonon matrix elements in the Wannier representation. So in this case, we basically have 3 objects again, the 2 Wannier functions, and then the deformation potential in the Wannier representation. And these objects are localized. So this means that if 2 of them, when they are far from each other, for example, one function is non-zero, but 2 other functions are 0 at some location, then the electron-phonon matrix element will disappear. So this is very good news, because this means that we don't need to calculate hundreds of thousands of matrix elements, but we only need to calculate a few of them. And then once we know the electron-phonon matrix elements in the Wannier representation, we can go back to any mesh in the Bloch representation. And here in this plot, I'm just showing an example of the spatial decay of the electron-phonon matrix elements in diamond. And this is for the 2 limiting cases. So the first case is when Rp prime equals 0. So in this case, it means that the Wannier function on the left and the localized phonon perturbations are located in the same unit cell. And in the second case, we have when Rp is equal to 0. So this means that the 2 Wannier functions, they belong to the same unit cell. So in the first case, the spatial decay is dictated by the localization of the Wannier function and is expected to be similar to the decay of the Hamiltonian matrix elements in the Wannier representation, while in this second plot in the second case, the spatial decay directly reflects the decay of the phonon perturbation in the Wannier representation and is expected to show a localization similar to the dynamical matrix. So that's basically the key idea behind the EPW code, that it combines the strengths of density functional perturbation theory and maximally localized Wannier functions to enable extremely accurate and highly efficient calculations of electron-phonon interaction. So basically what it means, we can start from a coarse grid. For instance, let's say we take a grid which is 4 cube or 8 cube, and we perform calculations the density functional theory and density functional perturbation theory level using the quantum espresso code. Then we use maximally localized Wannier functions to go from coarse grids to this Wannier space, and then we can go back to the Bloch grid, Bloch representation, and we can do it on ultra-dense Brillouin-zone meshes. Before showing the examples for going over the superconductivity in transport part, I just want to mention a special case, the electron-phonon interaction in the case of polar materials. So in this case, the system, so in this case, some electron-phonon matrix elements diverge as 1 over Q when Q approaches gamma. And in order to deal with this problem, what we have to do is to split the electron-phonon matrix elements into 2 parts, a short component, that a short range contribution, which is dealt with using the standard Wannier interpolation, and a long range contribution, which is dealt with analytically. And this is the expression for the long range contribution. So in practice, what we do, you subtract this term from the electron-phonon matrix elements, you perform the Wannier interpolation of the short range part, and after that you add up the analytical part for the long range contribution. So, and this details about this theory you can find in Carla's paper, Carla Verdi paper that was published in the 2015. So just to show how this works, I'm just showing you a first example for titanium oxide, and this is going to be covered in our first tutorial after the lecture. So in this case, we can see that the dots are density functional perturbation theory calculations, and you can see that the singularity is correctly captured by the modified interpolation scheme showing here in blue. So that's kind of this. So far, I have just done an introduction of electron-phonon matrix elements and how we can calculate them. Now we can go into details and look at some properties. And the first thing that I'm going to talk about is Phonon-mediated superconductivity. What I will do, I will briefly just give you a talk about Phonon-mediated superconductors, and then I will describe briefly the anisotropic Migdal-Eliashberg formulas for superconductivity. So as probably everybody knows, in a superconductor below a critical temperature, the resistivity drops to 0, and this property is important for many applications. The first microscopic theory of superconductivity was proposed by Bardeen, Cooper, and Schiffer in 1957. And what they did is the BCS theory starts from the assumption that there is some attraction between electrons which can overcome the Coulomb repulsion. And in conventional superconductors, the attraction is mediated by phonons. So basically we have the coupling between the phonons, the coupling between electrons with the crystal vibrations. So to get an idea of how this happens, we can look, for instance, at 2 electrons in the system. As 1 electron travels through the crystal, it creates a lattice distortion with accumulation of a net positive charge. This deformation causes a second electron with opposite spin and momentum to move into this region of the higher positive charge density. As a result, these 2 electrons become correlated and they form what is called a Cooper pair. And because there are many such pairs in superconductors, these pairs overlap very strongly and form a highly collective condensate. And at sufficiently low temperatures, the electrons stay paired together and can resist any kicks from the lattice. As a result, what happens is that now the system, the material can carry current without energy loss. So basically with zero resistance. Diagrammatically, we can show the formation of this electron pairing in this following scheme. So basically what it means is that the first electron emits a phonon that, and then goes into a state K prime. This phonon is absorbed by a second electron in the state minus K, which also goes to a new state minus K prime. So basically what effectively what happens is that these two electrons scatter on each other by exchanging a phonon. And in order for this scattering to take place, the later states must be unoccupied. And this is only possible in the vicinity of the Fermi level. Now, an important prediction of the BCS theory is the appearance of a superconducting gap in the single particle excitation spectrum of a superconductor. And if we want to understand this, we can compare the density of states in a metal and the density of states in a superconductor. So in a normal state, in a metal, all states are filled up to the Fermi level and empty above. Now, in the BCS ground state, the electrons close to the Fermi level are all bound in Cooper pairs. While individual electrons are fermions and they need to obey Pauli exclusion principle, Cooper pairs behave like, have boson-like properties, and therefore they are able to condensate into the same energy level. As a result of this condensation, this gap is formed within the normal valence band around the Fermi level. And basically we can see that this pinky, the density of states near the lower edge of the band, greatly increases to accumulate those electrons that have previously occupied states within the gap. And the important thing about the superconducting gap is that this basically gap corresponds to breaking up a Cooper pair. The gap has a temperature dependence, is maximum at 0 Kelvin and vanishes at the critical temperature. So this energy gap can be measured experimentally using single electron tunneling, optical reflectivity, or low temperature heat capacity. So our goal is basically to be able to estimate as accurately as possible the temperature dependent of the superconducting gap. And a first principle approach to calculation of the superconducting critical temperature and superconducting gap is the Migdal-Eliashberg theory. In 1960, Eliashberg proposed a generalization of the BCS theory that incorporated the theory of time-dependent electron-phonon interaction formulated by Migdal for the normal state. And the central point of the Migdal-Eliashberg formulings is the calculations of the electron self-energy, which consists of a sum of two terms, an electron-phonon contribution and the Coulomb contribution. So in this case, we are only writing the leading terms in Feynman diagram of the self-energy, and this is called the Migdal approximation. The neglected terms are of the order of the square root of the electron mass to the ionic mass. So in the system for which the energies of the phonons are of the order of the energy of the phonons and electrons are comparable, this approximation, which is called the adiabatic approximation, breaks down, and it is necessary to include higher order corrections in the electron self-energy. But the implementation of in EPW only relies on these two terms. So basically starting from this self-energy, and I'm not going to go into details about the derivations since this will really are too long, we can basically obtain two coupled nonlinear equations for the mass renormalization function and the superconducting gap, superconducting energy gap delta. And these equations are obtained under the assumption that the pairing occurs mainly within a small energy window around the Fermi surface, and that the density of states is approximately constant at the Fermi energy. And as you can see, the key quantity that enters in these calculations is the anisotropic electron-phonon coupling strength, which is connected to the electron-phonon matrix elements. Now, you may notice here that the Coulomb interaction was replaced by a parameter. This is called mu star. And in principle, the Migdal-Eliashberg theory accounts for both electron-phonon and electron-electron interactions, but the second term, due to computational constraints, is generally approximated by a semi-empirical parameter. The screen Coulomb interaction can be calculated, in fact, using the random phase approximation. And we have done this in one of our studies. So now, in order to, sorry, I also forgot to mention, so the temperature enters in this equation through this parameter I omega j, which are called the Matsubara frequencies. So you can see here this is the temperature. So what we have to do in order to estimate the temperature-dependent energy gap, we need to calculate these equations self-consistently at each temperature. And as you can imagine, since we have electron-phonon matrix elements, and if we want to properly describe anisotropic effects, this equation must be evaluated on dense K and Q meshes. Then second, we also have here the sum over the Matsubara frequencies that I mentioned. And in practice, in general, this is an infinite, in theory, this is an infinite sum, but in practice, this must be truncated, and typically due to computational limitations, we set this to 4 to 10 times the largest phonon frequencies. And then finally, I also want to remind you that based on the way that these two equations were derived, Z and delta are only meaningful for states at or near the Fermi surface. So let me just show you one of our recent examples where we elucidated the origin of the superconductivity in niobium disulfide using this anisotropic Migdal-Eliashberg theory, where in fact the Coulomb interaction was calculated ab initio using the Sternheimer GW code. So scanning tunneling spectroscopy measurements of this compound showed two pronounced features, one at around 0.5 and one at about 1 milli-electron volts below the critical temperature. So the critical temperature in this compound is 5.7. And these two features are an indications of a two-gap superconductivity. So for the case of niobium disulfide, the Fermi surface consists of three distinctive parts. So we have a disc-shaped hole pocket centered around gamma, and this has predominant SPZ character. Then we have a second cylindrical hole pocket also centered around gamma, and this has out-of-plane niobium D character. And then we have a triangular surface centered around K, and this originates from niobium in-plane or d in-plane orbitals. So now if we look at the superconducting gap, calculated superconducting gap on the Fermi surface, we can see that the gaps on the gamma Fermi surfaces have a narrow distribution, so it's below 0.6 millielectron volts, while in contrast, the superconducting gap on the K-centered Fermi surface is varies in a wide range between 0.5 and 1 electron volts. And now by comparing this distribution of the gap on the Fermi surface, we can conclude that the low values of the superconducting gap are found on those regions of the Fermi surface with out-of-plane orbital character, so on the S and niobium, while the larger values correspond to the regions with in-plane character on niobium orbitals. But what is more important, if we do such calculations at various temperature, and if we plot the delta on the Fermi surface as a function of T, we can see that the two gaps, we can see that at each temperature, the gaps cluster around two distinct values. So this will be the value for the gamma surfaces, and these are the one from the K surface. And from this gap, we can now extract the superconducting density of states, and we can compare it with the experiment. So as you can see in this plot, the agreement between our calculations and experiment is very good, apart from a scaling factor that we had to introduce. And this confirms that the peaks around 0.5 and 1 millielectron volts are in fact the same as in the tunneling data, and they can be associated to the gamma and to the K-centered Fermi surface, to the gamma and K superconducting gaps on the Fermi surface sheets. So that's kind of just the brief review that I had on superconductivity. We are going to do talk more about superconductivity in our second tutorial of the day. So finally, the last topic that I'm going to talk about today is phonon-limited carrier mobility, and this work was done by Samuel Ponce while working in Oxford with Feliciano Giustino. So carrier mobility, we know, quantifies how fast an electron and hole can travel in a metal or semiconductor when subjected to an external electric field. And since the mobility plays a central role in semiconductor devices, considerable efforts are being devoted to make accurate predictions of carrier mobilities. So when carriers, either electron and holes, propagate into a material, there are a number of scattering processes that can take place. So we can have lattice scattering, impurity scattering, such as defects and dislocation. We can have scattering from ionized impurities, and also if there are a lot of impurities, they can interact with themselves. And among these scattering mechanisms described here, only the scattering theory of charge carrier by phonons has been developed far enough that predictive calculations are now possible. So in this last few slides, I'm going to focus on the derivation of the linearized Boltzmann transport equations that enables parameter-free calculations of phonon-limited mobilities in metals and semiconductors. And to start with, we can look that in the steady state, the electric current is related to the driving electric field via the mobility tensors. And one can show that the electric current is equal to an integral over the occupation factor times the electron band velocity. So in this case, what we need to find the occupation function f and k, which in the absence of an electric field reduces to Fermi Dirac distribution. So now, since we are interested in computing the mobility, we can just take the derivative of the current with respect to the electric field. So basically, this means that we need to evaluate the derivative of this distribution with respect to an external electric field. And this is basically the linear response of the distribution function to the electric field E. Now, this quantity, this linear response of the distribution function to the electric field can be calculated starting from the Boltzmann transport equation. And I'm not going to go into all the details here, so I would recommend that you look at this nice review that Samuel has just published. But just kind of to give you a quick understanding is that the right-hand side in this expression is the collision term of Boltzmann equation for a uniform and constant electric field in the absence of temperature gradients and magnetic fields. And the left-hand side is the modification of the distribution function arising from electron-phonon scattering in and out of the state Nk by via the emission or absorption of a phonon with frequency omega q. And these scattering processes are shown diagrammatically in these figures below. So now this quantity, so now this quantity can be computed starting from the DFT. Now we can do a further approximation, which is to linearize the Boltzmann transport equation. And what this means is that we expand f and k, and for small electric fields, and we can keep only the linear term in the electric field. So in this case, we are getting the following expression. And now if, so in here, if I cast the four processes that I shown diagrammatically on the previous page, we'll get this, this equation that I'm showing here. And you can notice here that, so these are basically the four terms that correspond to in and out scattering from the state Nk through the emission and absorption of phonons. You can also notice that here we have f and k, f and k plus q, and not the Fermi-Dirac distribution function. And second, you can also notice here that we have the electron-phonon matrix element. So in order to calculate this expression, we need to evaluate the electron-phonon matrix elements at dense K and Q meshes. Now the final step, since you remember we want to calculate mobility, is to take the derivative of this Boltzmann transport equation with respect to the electric field. And we can obtain an explicit expression for the linear response of the distribution function to the electric field, here having defined the relaxation time. So in this expression, this tau and k, this is the relaxation time. And this expression is called the iterative Boltzmann transport equation. And in order this equation, and since we have here f and k, but on this side you can see that we have f and k plus q, this equation needs to be solved iteratively, needs to be solved self-consistently. So we can imagine that it's quite expensive, and the solution, its solutions, it will give us this linear response coefficients, which are needed to calculate the electromobility. A simpler approach, if we neglect this term on the right-hand side, so basically all this part here, we can, what we are getting is that the response, the change in the the linear response of the distribution to the electric field now reduces to a simple expression. And in this case, we have Fnk and Fnk not on both sides. So this means that this doesn't have to be solved self-consistently. So I would also, I guess I should also mention, so we are calling this the self-energy relaxation time approximation because the term on the right-hand side depends on the relaxation time, which is the inverse of the, which is proportional to the electron-phonon self-energy. And that's why we call it the self-energy relaxation time approximation. And in this approach, the electron-phonon mobility now can take this simpler expression that I'm showing it here. Sorry, I have to, I guess, to speed up a bit, but I'm only having a couple of examples to show. So now let's first see how the Boltzmann transport formula is performed. And this is the example of the intrinsic carrier mobility in silicon. In orange and blue are the electron and hole mobilities, where the lines are calculations and the dots are experimental data. So we can see that in the case of holes, the DFT results show some an overestimate. And the reason for this is very specific to the case of silicon. It turns out that one of the effective masses in the valence band is poorly described both by the DFT and the GW. If we now replace this effective mass by the experimental value, we get this dashed line, which is in very good agreement with an experiment. And this is a bit technical, and I'm not going to go into details, but it shows the impact of a lot of different approximation on the mobility results. One thing that I would want maybe to highlight here, that in case of silicon, the difference between the iterative BTE and the SERTA is really not that big. So finally, the last example that I want to mention is a new study done by Samuel and his collaborators, and this concerns gallium nitride. So the results of this study are summarized in these two plots. So we can see that both electrons and hole mobilities, the results are in theoretical results are in good agreement with the measured values. But one thing that you should notice is that the hole mobility is nearly 2 orders of magnitude smaller compared to the electron mobility. And because of this, this is a fundamental obstacle towards realization of p-channel transistors made of gallium nitride. In this study, Samuel explained the origin of this hole mobility due to a combination of heavy carrier effective masses and a high density of final electronic states available for hole scattering via low energy acoustic phonons. So using this understanding, they predicted that the hole mobility of gallium nitride could be increased by reversing the sign of the crystal field. And this is shown here in this. So basically, by doing a crystal field inversion, one can lift the split of states, the split of hole states above the light and heavy holes as shown in the figure. And this reversal of crystal field splitting may be achieved by a biaxial strain or a uniaxial compressive strain, as summarized in this figure DNE. So for instance, we can see that a 2% biaxial strain, one can increase the hole mobility by 230%. So these results are very interesting, and some experimental collaborators of Samuel and Feliciano at Cornell are currently working on confirming these predictions. So, okay, I'm almost finished. Just in the end, I want to highlight some of the EPW capabilities. I haven't talked about all things that we can do with EPW, but basically one can calculate electron and phonon line widths, scattering rates and lifetimes, electron and phonon spectral function. As you saw, I discussed this. We can do electron-phonon vertex in the presence of Froelich interactions. So this is characterized for polar materials, electron-phonon coupling strength, phonon-limited optical absorption, anisotropic superconducting properties, and electronic transport properties using the Boltzmann transport formalism. And among the EPW features, I would say currently it can support both LDA and GGA functionals, and it can now support non-conserving and ultra-soft pseudopotential, spin orbit coupling calculations, time reversal, symmetry, and as we saw, I'm repeating again, polar divergence is correctly interpolated. And just to remind you that EPW is integrated into the quantum espresso code and relies on the Wannier 90 package. It is MPA parallelized, and we have a test farm for stability and portability of the code. And as future directions, and some of them hopefully will be released sooner, some 1 or 2 years, but the code can calculate mobility at finite magnetic fields, electron-phonon interactions in 2D materials, and Samuel has also been working on a high throughput electron-phonon computations with AIDA. So all these 3 things are stuff that Samuel has been working on. Then hopefully in the near future, we are going to have parallelization over the G vectors. And these are more like long-term project that hopefully will be available. The development will be available in a year or so. Spin transport that Samuel is planning to work on. And on my side, I'm planning to work on fully ab initio Migdal-Eliashberg approach for superconductivity. In other words, to properly take into account the Coulomb interaction when we are solving the Migdal-Eliashberg equations. You can download all the code. You can download the code, including the latest version, from the GitLab page of the Quantum Espresso. And currently, you can find information about the code, the input variables on this website, but very soon it will be, we are now in the process of making a new website that hopefully it will be more reliable, more better than what we currently have. And this will also include, the new website will also include the forum. So finally, I just want to acknowledge the people that were involved in the work that I presented in this, the development of the code that I presented in this talk. And this is Samuel that has worked on the transport module. Then Carla that has done the electron-phonon vertex for the polar materials, and Feliciano that has started the whole project and continue to work on the EPW code. And of course, the agencies that have given us money and are continue to give us money to work on the EPW. And in the end, I just have some references that are divided on methodology, software, and applications that you may want to look at. Thank you.